So we are live. Let me just quickly check here. Yeah, so it will start in a moment, I guess. Maybe. Okay, guys, so welcome to my channel and good morning, good evening, good afternoon, whatever the time zone you are in. So today we will be solving today's LeetCode problem, and this is a fresh, unseen attempt. I haven't seen this problem before, and I'll be solving this problem. I'll be reading the problem, I'll be listing out what is required, I'll build a logic which is called algorithm, and then that algorithm will be converted to pseudocode. Then we fit that pseudocode to the constraints of this problem, and we'll try to create a successful solution. Now, that solution could not be the best solution because obviously we are spending a lot of our time in understanding the problem and attempting it from scratch. So that's it, guys. I'll just check if live has started. Yes, it has started. So if you have any kind of questions, you can just put here in this chat. And yeah, that is it. So this is a hard problem. First of all, happy Diwali to everyone who are in India. And basically today I spent my day chilling, and so now I was free and I had nothing to do, so I just started this live stream. And let's maintain the streak which we have. And this is the ninth day of solving live lead code attempt. Okay, live lead code problem. And let's get started. So this is my iPad screen, and I'll be reading the problem and solving the question now. Okay, so first thing first, let's go ahead with the problem statement. So it says um, minimum total distance, wait, minimum total distance traveled. So we have to find minimum total distance, okay, minimum of total distance traveled. All right. So what's the question about? There are some robot. Again, it's a hard problem. I wished that I could get medium problem today because it's Diwali, but no worries. We will be solving this. Okay. So there are some robots and factories on the x-axis. So there is this horizontal x-axis, and there are some robots and factories. Let's call it R and let's call it F. You are given an integer array robot. So you are given. Wait, let me just. So I am given robot array, which basically will contain the position of ith robot. Okay, so it contains the position of robots. You are also given a 2D integer array factory. So we are also given factory, which is a 2D, two-dimensional integer array, where factory of j is actually, it should be an array because it's two-dimensional. So the first index, basically the first index will be the first row, and it will be it will have some columns, and they say it has two columns, position I and limit j. What does these two means? Indicates that position I is the position, indicates that position j. So for the jth thing, it will be j here, sorry. This is also j. For the jth index, position I is the position of jth factory. Okay, so there are some factories, right? And position of j is the jth factory, and that jth factory is can repair at most limit j robots. Okay, so this is the position of factory, and this is number of robots it can repair. So basically each factory has some capacity to repair robots, right? So the positions of each robot are unique. So these positions are unique, means robots are not standing at, no two robots can be at the same place. This position, all of these positions are unique. Okay, note this thing, unique here. And the position of each factory are also unique. So these factory locations are also unique, means no two factories can be at the same location. Suppose this is a factory F1. So there cannot be factory F2 at the same place. Factory F2 should be somewhere else. Maybe here, or maybe here, or maybe here. Makes sense? Note that a robot can be in the same position as a factory initially. So yeah, these basically at one factory there can be a robot. That's completely fine, but this is not fine. At one location there could not be two robots or two factories. At the beginning, basically it is already given in the problem. The position of each robot is unique and the position of each factory is unique, but robot and factory can be at the same place. This is allowed. Okay, this is very simple stuff. I think every one of you have gotten this. Now all the robots are initially broken. Oh man. Oh, okay, sorry, it's not that broken. So it's basically they are faulty. So all of them are initially broken. Okay, this is the third information. All robots are broken. Okay, so they are broken. Got it. They they keep moving in one direction. All right, so they will move in one direction. This direction could be this direction could be positive or negative, as I read from here. Negative or positive direction of the x-axis, right? So robots can move, they keep moving in one direction. It means that it could be either one of them. So you have to really make one decision out of this, which direction they will follow. And after that, you will get either this direction or this direction. When a robot reaches a factory that did not reach its limit, the factory repairs the robot and it stops moving. Okay, so if it reaches to some factory, maybe here, so it gets repaired. If capacity of a factory is not full, basically it has already repaired. If it has already repaired the limit J robots, so it can't repair this robot. Makes sense? Now at any moment, you can set the initial direction of moving for some robot. Okay, at any moment, you can set the initial direction of moving for some robot. Okay, so you can set the movement of any robot. So you can choose basically whether you want this robot to move this side or you can want this robot to move this side. But the thing is that you can do this anytime. You can anytime decide that this particular robot has to move there and this direction or this direction. But once you have decided that, uh, this is the thing, they should keep moving in that direction only. Basically, once you have decided a direction, it should follow that for entire its journey, right? Your target is to minimize the total distance traveled by all the robots. So your target is to minimize the total distance. Okay, so obviously robots will travel to get them repaired, right? And you have to minimize the travel time. That is it. Now, these are the constraints. Basically, all robots move at the same speed. It means you just need to worry about the length of path covered because speed is same for each of them. So, larger the length, larger will be the time. But we don't have to care about the time. We have to minimize the distance only. So, it doesn't matter if they move at the same speed or some robot is like ultra super faster than others because we have to minimize the distance. Or does it matter? No, so this matters actually. Basically, if they move at the same speed, it means that some ultra super powerful robot cannot outrun the slowest robot, slowest rabbit robot. So basically, they move with the same speed, means that move cool. If two robots move in the same direction, they will never collide. If two robots move in the same direction, they will never collide. Okay, okay. So let's say if this robot was standing still, this was moving, so it can just pass this guy. They won't collide. Makes sense. If two robots move in opposite direction and they meet at some point, they will not collide. So otherwise, this case is also there. If this guy is moving here, this guy is moving in this direction. If they pass each other, they won't collide it. They can just simply pass. So it's a two-lane roadway that anyone can overtake and anyone can like pass each other in opposite directions. Now, if a robot passes a factory that has reached its limit, it crosses it as if it does not exist. So this is an important thing. Basically, if a factory is has exhausted its limit, basically its limit is zero now, the robot can simply pass it. But if it had some limit, if a robot is passing, then it is a must. If let's say it has 10 limit, then it's a must that the robot should get fixed here. It won't go to the next factory to get itself fixed. It will be fixed here only because you see here, um, whenever it reaches a factory that did not reach its limit, the factory repairs the robot and it just settles down over there. Now, if the robot moved from position X to position Y, the distance it moved is Y minus X. Makes sense if it moved from position X to position Y. Y could be here also. So the distance will be basically the modulus of X minus Y or Y minus X, which makes sense, right? Nothing, nothing fancy here. Okay, so now you have to minimize the movement of robots. So first thing first, what we can do. So in our hands, these things are there. At any time, we can ask robots to move. Second, direction once decided, won't change. And in layman terms, basically, uh, when they pass through active factory, they get repaired on their own. Now, guys, at any time we can ask robots to move and direction will not change. So basically, we have the power to move the robots, right? Move these guys either to this side, wait, either to this side or to that side. This side, that side. It's up to us. Now, let's look at the examples here. Basically, these are the positions of robot and the factories are here. Now, 046, 046. Now, factory is at. Okay, so here it has 2 as a limit. It can repair 2 robots. It can also repair 2 robots. The first robot at position 0 moves in the positive direction. It will be repaired at the first factory. So it moves in this direction. It will be repaired over here only. Makes sense. Second robot moves in negative direction. So it will get repaired there only. Third at position 6, this guy will be repaired at the second factory. So it was repaired at the first factory, this guy, and this will be repaired at the second factory. It does not need to move. Now there is one question which my mind is asking is about this. If initially they are in this configuration, then this robot will get repaired automatically, or when we want. Basically, we can let it wait, we can let it go there, and some other robot will be repaired here. So limit of first factor is 2. It fixed 2 robots. Cool, it fixed it, and it fixed one robot. So this was the kind of minimum distance they have traveled. Now the only question is here, like if some condition like this is in, so without even starting, this will get repaired, or we got some control over this, right? Perfect. So how I see this, guys, basically I see this problem as like, mm, I see this like there are these robots, and there are some factories, right? I'll call them F1, F2, F3. For each robot, there is some distances D1, D2, D3, and robots can change their locations. That's fine, but yeah, this distances is the final thing. Basically, they had to get repaired, and let me think if it is guaranteed to get all of them repaired. Yeah, so it's mentioned here. Return the minimum total distance traveled by all the robots, distance traveled by all the robots, right? And test cases are generated such that all robots can be repaired. So it is mentioned in the problem that all the robots can be repaired. So we don't need to worry about that case. So basically it is guaranteed to have a solution. So basically all of these robots will be sent to some factory at the end, right? And that's the case here. So this will be the case for this F1, and for this part, for factory 2, we will have same set of D1, D2, D3. I'll call this D1 dash, D2 dash, D3 dash. For this we had D1, D2, D3. And for this also we had D1 double dash, D2 double dash, D3 double dash. Now, this is for the first one. This is for the robots get repaired over here. This robot gets repaired over here, and this robot gets repaired over here. So here, mm for the first robot R1, we got three options: D1, D2, D3. Sorry guys, we got D1, 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 and this will be D1 dash, D1 double dash. And depending on what we choose, so this is basically I'm discussing the brute force approach. And depending on what we choose and the limits of these factories, for the next one, for the next robot, which is R2, we got limited options, right? We got limited options. So here we started with R1. It might be the case that we started with this particular robot, that could be R2 as the starting point. Why? Because choosing these as starting points, choosing the starting point, like choosing so basically this could be R2 as well, this could have been R3 as well, which will decide the further scenarios. Basically, if you choose this R1 to get through this factory, after that the entire configuration had changed for F1, and likewise F2, F3 as well. Like they depend on F1 at some, they don't depend, but basically they these resources are kind of has to be utilized by these two, right? So F1 will be changed here, F2 will remain same, F3 will remain same. That's a separate thing. Now here also we got two options, whether to go with robot 2 or to go with robot 3. And for robot 3 or robot 2, we got some more options here. So you see, this is how it is progressing, right? And then we will kind of, if we follow this particular recursive tree, at the end we will generate all possible ways, get them repaired, and minimum length traveled is answer. That is the pure recursive solution. And what are the constraints here? So robot length, factory length is of the order 10 to the power, and factory zero length is 2. We know that. Basically, one first is the position of factory, and j is the basically limit of the factory. Then you have this thing, 10 to the power 9 is the value limit for each of them, and position could be negative as well. So yeah, that is kind of makes sense, right? And limit j is basically a factory could have maximum mm, n kind of limit. That is also there. So this is a tense thing. Now let me think about how much time this solution will take. So let me just uh, write the solution again for you. So basically we have, this is our starting point. This is the recursive approach. I'm trying to just, this is basically brute force. I'm just trying to generate all the possibilities for these robots to get repaired. So now we can start with, let's say there are n robots. So we can start with n options. Now notice here that the limit could be 0 as well. So it might be the case that a factory is just void. So you cannot repair any robot here. And one more thing, guys, I did not get the proof of this thing. Basically, if both of them are at the same location, you still have the choice to move this robot to some other factory. That is completely fine. This is what I assume. Basically, it's not that if this robot, when we started the process, if this robot is at the factory, it will surely get repaired. Basically, this is not a hard thing, hard saying here. Like when a robot reaches a factory that did not reach its limit, the factory repairs the robot and it stops moving. But for that, I need to check one more example here, which is given. Now, this is the position of the factory, and this is the position of factory 2, and the robots are here. So what they have done is basically very simple step, to be honest. What I am concerned about is, let's say it's is that, uh, let's say if there are two factories here and here, and some robot R1 is here, some robot R2 is at very far location, so it will come to here, and this has two options. It could go here, it could go here, and this could also go here. So it will, if this guy thinks to go over here, this guy can grab this, right? So in that case, the distance will be quite less. If not, this guy will go, if this guy goes here and this guy will go here, in that case, distance will be like a lot increased, right? Because what you could have covered in this and this, now you're covering this, which is basically longer than these two itself, and plus you also add this cost. So obviously, if we do it recursively, we will generate each and every possibility. And the thing is, like, which I'm still having some doubt, like, can some robot skip a factory? Because if we go by this way, it can. So this robot can skip the factory one and go get it repaired at factory two. If this factory still had some resources, that is not clear in the problem, and I should literally see that. When a robot reaches a factory that did not reach its limit, the factory repairs the robot. So I think the robot has not got any choice. It has got just one thing, like the direction in which it can move. Now, one thing is here. All the robots are initially broken, they keep moving in one direction. Let me just see, man. I have not. I think I have misinterpreted some part of the problem. What we are given with robot locations and factory locations with their strengths. Now we have the possibility to assign directions for each one, because what they have done is, so it moves in positive direction. So they have decided, right? Yeah, it is not given that it should move in positive direction or something. It will be okay. So we have the options to just decide. So we can just decide the direction of movement. So basically, it's like this. So we have, let's figure it out. We have some set of robots, and we can decide the direction. So here is this, two direction possible for this, two direction possible for this as well, and two direction possible for this as well. And now when we decide a direction, so basically we will generate 2 to the power n directions, directions like what we will say, configuration, right? What do I mean by that? If there are three elements, we will generate eight possibilities. It will be like this. If you call 0 for the right direction, it will be, it can be 0 0 1 1 1 0. Basically we are deciding the configurations of movements. So it could go up to like 2 to the power n here. And so there are 2 to the power n directions. And now we compute here, compute the time taken by each configuration. If all robots are allowed to move, from t equals to 0, we will get, and the minimum of it will be the answer, in my opinion. So basically the movement is not under our control. In our control, it should be the directions of each and every robot. So we can decide which direction they can move. So clearly there are 2 to the power n directions, and n is the of the order 2 to the power 100, which is basically 2 to the power 10 to the power 10, which is 10, 24 to the power 10, which is basically 10 to the power 30. So 2 to the power 10 is 10 to the power 3, and 10 to the power 30 will be just this configurations of movements. And when you just check the time, it will again, I guess, take order n, at least order n. So it is of the order 10 to the power 32 or 33, similar to that, or 34, which is very much far away from 10 to the power 7, which is acceptable solution at lead code, right? So now we need to apply something else. We need to have we need to apply domain specific knowledge to find a greedy solution, or we can optimize this recursive approach by finding something known as dynamic programming, something known as computation thing. You have to break the problem into independent subproblems, and you cache their results, and these problems should be repetitive, and you cache the results and you kind of get the solution. So and the other approach was basically being greedy. Greedy means some kind of knowledge you have about this problem which reduces the effort. right? Which ensures that you it will some strategy which you have, which is guaranteed to work in this case. So the our goal is to locate relocate these guys to factories. Factories has let's think it like this. Factory has got some seeds, and as soon as this passes through this factory and it sees an empty seat, it will just sit over here. So once I decided that this guy will move in this direction and this guy will move in this direction and this guy will move in this direction. Okay, so this guy, if it tries to move in this direction, then it can never get repaired. So for you, because there are enough seats for everyone. Right, as it is said in the problem, now you have to just think of their directions. Right. So now, depending on what you have uh, guided them to move, they will be reaching here. Right. So let's say there are more factories here. Now, so when this guy started and there was just one seat. Now these two guys started. What happened with this guy? So let's say there was only one seat over here, and this guy was close to this particular thing, so it directly gets over here before this guy could reach, and it kind of occupies this factory. Now the factory is full of its limits. Now this robot will be like cheated. Basically, it was coming to this particular node, this particular factory location, but somebody else came before it because they were near to this, and since they move with the same speed, the robot which is closer to the factory will reach first. Right. So now this robot will go on in this direction, right? So guys, this is very important. Like the configuration which works here. Uh, First we have to generate all the solution. All the solution means all the relations of this array. Basically, there are two possibilities each step. We have to generate all the possibilities, and the one which will ensure that they fit, they are prepared. And among them, you have to find one which does it in the each step. So I think about greedy solution here. Greedy solution means like some sort of strategy which is guaranteed to work. Okay, so but we have got many participants, right? We got many participants. What we can get is basically their distances from each and every node, each and every factory. We could have calculated that. Obviously, direction matters. Could reach the node in two two steps. Yeah, let me just. Some robot could reach a factory. It is at the distance 2 of it, and some robot this is at the distance 1, right? Now the thing which hunts you is the possibilities, like what are the possibilities for each and every solution. Okay, so Diwali is really guys. I can the firecrackers. Anyway, so if we try to solve this, how can we do this? Basically, there are many factories over here. In this line, there are many factories. Now you have to find the one which is the minimum, guaranteed to be minimum. Now, there's also one thing which kind of guides you to think like there is no greedy solution. Is that there are a lot of past possibilities which is impossible to get some greedy things out of that, right? So I see the two challenges here. First thing is to configuration of directions. Can you pre-decide that? Means you generate a direction configuration which is guaranteed to work Let me think. Now we know the capacities of each and every one. So it could be 0, 1, and 1. If you know these things and you kind of go in this direction and try to compile them. So here we have 1, here we have, before this we have 1, and before this we have two factories, including this, right? So I just did a prefix sum of factories, so we know this particular pattern, and standing at any factory, we can guarantee it is guaranteed to tell like what could be the configuration. So let's say if we have yeah, let's say we had two repair spots here, so it will become three. This was one only. Now let's say we had two robots in this place. Now these two guys can, and if we check the prefix value before this, now these two guys cannot get repaired in this direction for sure. Why? Before this, there's only one seat for a robot to get repaired. Now in this direction they have two seats, right? So if these guys want to get repaired, and you have to minimize the effort needed. There's one thing we can do is the basically we can allocate each one of them at their respective locations at some particular factory. But when we do that, when they are inside their factories, basically then we decide the directions of each and every particular thing. So yeah, basically how can we go, man? Mm. So greedy approach, we can have this strategy like we always try to go to the nearest factory. So let's say we have distances from each and every factory here, and we try to go to the nearest factory. But that could not be a good solution, because some solution could be like this, that you, instead of this, where you could get basically, instead of this where you could get like five steps, five length to reach to this factory, you actually chose to be here, which is at 8, which is at the 8 distance from this location. Why? Because it made it easier for this guy, which was quite some distance away. Let's say it was some 10 over here, so 15 plus 3, 18. So if it now it joined here, it's now 15. So now the total cost will be 15 plus 8, which is 23. And other way around, if this guy had chosen this, it could have been 5 plus 10 plus 8, 18, or 8 or 5. So it is the same in this case. It didn't really generate a difference. Now when can a difference be there? Yeah, basically, can is it possible to choose a location which is farther and is it is still beneficial? In this case, it wasn't, because no matter any one of them can travel the same distance, right? And this guy could have its own this guy could its own other options here. So it could choose from there. So I'll say there are two competitors for this location. So it is any one of them joins this, it doesn't matter, right? This guy joined by traveling X distance. This also joined by traveling X distance. Now there was only one seat, so this traveled X here. Now this guy, uh, for this guy, basically, if I give this chance to this guy, for this guy, the next nearest was at 10, right? And but for this guy, the next nearest was at 20. Or if it was 10 from here, maybe this way you can say it will be 10. And this way you can say it will be 20. So in that case, you have to really choose which guy will you give it the opportunity for. So you are going 20 over here and 10 when you use this. So I could do this. I'll choose this guy to go over here and this guy to do this part. Why? Because this part is not traveled extra, right? If this guy has traveled to here at the same time, if this was like 100 and for this guy, the factory could be at 50 that side. I'm really puzzled at this problem. Let me think if any one of you is with me. I just saw this question, 20 minutes to understand questions, but unable to memorize it, then solve by seeing solution. Yeah, that's cool, man. Basically, 20 minutes to understand, 1.5 hour to solve. Yeah. Yeah, that's how it works for hard problems. Yeah, it took 20 minutes. Yeah, I understand that. Basically, the problem statement is not easy. It is kind of detailed. So, yeah, makes sense. Now, let me just again, this is so painful to like basically capture all the cases in mind. So, I'll just use R and Fs. So, these are robots, and there is some set of distances for this guy, some set of distances for this guy, and some set of distance for this guy. Hmm. I think greedy solution we should really sometimes it is not possible to come up at the greedy solution because the problem is too much tweaked. Here you have to just think about distance level, and by distance you have to think like basically if there are think about in this way. Basically there will be a final configuration, right, which will say that this factory at the end, when everything was successful, we got robot number 7, robot number 8 over here. At the end, we got robot number 1, robot number 2 over here, and robot number 3, robot number 4, robot number 5, robot number 6 were all here. And this was giving me the least traversal. So, what is this about? Basically, now the factories are choosing robots. Think it like that way. So if these factories are choosing robots, in that case, what should be the case? So hmm, now each factory has got kind of, let's say the capacity of it is L, the limit. So it has got L options, right? And once it can choose L options, right? And then this factory can also choose some options. This factory can also choose some options. Now, so what all these factories have to coordinate to decide the direction of robots, which robot they want, because for robots, it's very much easy to reach any factory. Basically, they can travel across these things, right? Across this direction, right? So they can reach to any factory. So this is factory 1, this is factory 2, this is factory 3. So now these robots can reach any factory, right? With some cost. Obviously, there is some cost. So for each factory, we can have a cost list for each robot. I'll call this C1, C2, C3. For each robot, we have this, right? And now we have to choose. This is our first robot, this is our second robot, third, and fourth, like that. So this is the thing, man. So now you have to choose which one you will color up. So for this line, you can color up this, or you can color up this, or you can color up this. For this line, you get to choose one option out of this. So this will be n length, this will be n length, and this will be n length, right? So there are two constraints here. Here you can choose basically um, there are two constraints. First thing is like the capacity of the factory it's is L1, which is L2, and which is L3. So basically you can just select L1 number of so this will be like NC L1 multiplied with NC L2, and basically that will get coordinated. Oh, that will get basically if I select some rows over here. If I try to think about all possibilities, in that case, so these values, let me write that. Let me take an example, then only I could be able to deduce it. So it is 046 and 2, 6, and the limits are 2 and 2. So I have written the test case over here, and you can see like for 0 we got. Okay, so I'll just write the cost one thing. So for all the robots, these are the robots, and I'll write the cost for traversal. So this is at 0, so this will take 2 steps, and this will also take 2. This will take 4. I'm taking modulo by subtracting these guys, right? And this will take 6. This will take 2, and this will take 0. Right. Now I can select 2 nodes from here and 2 nodes from here. Okay. So for this guy, we have to choose one of these, right? One of these. There could be more such factories, right? And there could be even more robots. But what we'll choose, we cannot simply choose the lowest one, right? Because there might be some case like this at some place this factory costs 1 step to reach, but this factory costs like 100 steps to reach. So in that case, and you already exhausted your limit of 2, right? So that's the case, man. You got limit as well, that you could select some level of some level of nodes. Actually, I'm getting some kind of call. just end it. And yeah, sorry. Oh, it hurts if you cannot solve this, but unable to memorize it and solve by seeing solution. Okay, stay with me, guys. I'll try till my end, till my last breath. Okay, so it would be kind of fun if I stay with this problem for 4 hours. Just kidding, guys. Hmm. There's some kind of crackers. People are just okay. Just forget about these things. So basically, yeah, I'm talking about that. You can select maximum two two robots in this array, and you can select maximum, let's say, two here also. So you need to be very much you need to consider these cases as well, where you got, like, if you selected this factory, you could have costed one, and here you could have costed 100. So it's like basically choosing some elements from here and choosing some elements from here, right? So, and if you choose some elements from here like NC, let's see, if we chosen NC L1 elements for this guy, those L1 rows are occupied. Now let's say there are now this L1 could be not L1 actually exactly, this could be like NC. It is even possible that we do not give this any robot at all, we just give it to some other factory, right? So in that case this could go up to, yeah, so this could, there could be a variable thing basically, L1 minus X. So we actually have give allocated X, um, we actually have allocated X robots. So basically we can go to maximum till L1, and so it is, let's say we can select 0 robot. So we can send robot 0, we can send robot 0, robot 1. Now we have more robots, let's say, so we can send 0, 3, 0, 4. So this will be basically NC. So this is basically NC0. This will be NC1, NC2. This will be NC1. Similarly, NC3 all the way up to NCL. And once you select one robot at this particular factory, there's one more case, like you select no robot, which will be NC0. In that case, from other factory, you got to select. Oh, that's a similar thing. Yeah, basically, I cannot think greedy will help here, because first thing is to consider, man, what can I do here? Basically, if we select one, then we kind of exempt 100 from the total solution, right? That makes sense. Definitely it does. So yeah, I am completely blank at the greedy solution here. Now let me just think about recursive solution. The recursive approach was to what was that? Basically the recursive approach is this. So there are some 100 factories and 100 robots, right? We have to put the robots at here, these factories, based on their capacities. Hmm. Right. That is true. Now for each robot R1, we would use this thing. Now for robot R2, this entire space will change because this robot will get placed somewhere here or here, and yeah, the capacity of each one of them will reduce. So this will get reduced. Fair enough, right? Here also, here are n possibilities. Here also we got n possibilities. This is just getting multiplied, guys, and it is a n to the power n solution, right? Can this be memoized? Basically, the configuration of each factory. No, it is difficult to memorize it because this is way too long, right? For each, basically, this could go up to 100 indices, and these values can go up to, that's also weird. um, these factories can contain, let me just check here. Hmm. So the limit could go up to n. Okay, so this is also an interesting thing. Basically, the factory's limit is kind of fixed. Yeah, basically it could go up to n here. So this is really bad. So all of these factories can accommodate at worst, and so the configuration will like kind of go in this way only. Yeah, so n. So if you try to do cache, so caching is kind of recursive only. We haven't broken down the problem. It's like you have placed R1 and now you're placing R2. So what kind of problem you're solving? So there was some factory configuration earlier. After placing R1, you'll get some other configuration. Yeah. But this approach and these configurations are basically independent, right? So these configurations itself can go up to n to the power n, which is 100 to the power 100, which is like crazy, 10 to the power 200 complexity. So this is dp, but this is dp, but this is not efficient enough. Now let me think about some cases here. At the end, a robot will find its piece somewhere, which is kind of the best possible thing for it. It could have gone other ways around, right? So let's say we, at the end, we have answer of steps. That, yeah, brute force is ready here, which is basically 10 to the power 200 order solution. But we cannot go like that. Okay, let's go step by step. If there is one robot and we have three choices, it says that the factory 1, factory 2, factory 3. It's got 0 capacity, it has got 1 capacity, it has got 100 capacity. So this guy could go here, 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 here. So it's a very simple solution for this. So this guy will go the one which is nearest to it. So the distances are given. This is why it is holding one, having a limit of one. This can prepare one robot, but it is at the location 10 to the power 3 steps away from here. And this is why it can accommodate 100. It is at the location 10 meters away from the robot. So what do you think it can go? So this guy has two options. It has gone for this part. Now things get interesting when we have two folks here, and these two guys can now again visit three factories. Here it has got one capacity, it has got one capacity, and it has got one capacity. And let's say this takes 10, 1, and this takes 5, right? And this takes, yeah, direction doesn't really matter. So I'm just taking absolute distances. And for this guy, it takes like, let's say a 5, 4, 2, 4 and 6 steps to go to these, right? If you are just thinking about this guy, for which the factories are at these distances, for it is 2, 4, 6. If you just think about this guy can go to the factory this can go to the second factory, because obviously it is at the one location and it just needs to travel only one step. But about this guy, when you decided to take this got out of the option, because this has a space of only one bot. So this is now kind of the second slot is filled for this. It must choose one of these. So it's 2 and 6. So you go 2. So you get 1 plus 2, 3 as a solution. Had it been other way around, um, yeah, let's say it was 10, 1, 1. So in that case, you choose the third one. Third one gets omitted here. And this guy chooses, and let's say this was 1. So the other guy, for other guy, this got omitted. Right. So when you choose a particular index, this is really painful. For each city, we have some cost for each node. For each factory, we have cost for each and every. Let's say even if we sort it, the top performing the shortest path nodes, right? In that case, what can we do is R2, R3, R2, R2, R3, R2, yeah. So these are the basically top values. This can exempt these nodes, right? Now, if I try to, yeah, this can benefit this particular node at value 1, but it might be the case that R3 is relieved by this node by 0, so also 0. So this means, okay, so I'm not using the fact that the positions are unique, right? I'm really not using it. So guys, I got a missed call from okay, how can I utilize everything? Just a second. 0 R3, 1 R3, 2 R2. Again, I'm going greedy only, and I guess greedy won't help here. So first thing first, guys, greedy can help. If greedy could help, this should not be 10, 100. Basically, if the constraints are like this, it means greedy is really very hard or not possible. So I should change my approach to recursion and DP only. So in that case also, how can I memorize this? How can I break this problem? Basically deciding there are n people and c chairs, and you have to locate these n people to c chairs, and for each chair they have some distances. So you have to locate n people to c chairs such that the final configuration is minimum. So we got n people to place c chairs. What do I mean by c chairs? Let's say some factory, and all these things are distinct. What does that mean? Basically, it means that a factory, this is a factory and this is the robot. This is the factory and this is the robot. If these positions are unique, it means that these two guys will never stand at the same place. There will be some kind of, and if some factory, if they got, if they go to the same factory, in that case, if that factory is here, this guy will grab this guy will go this. And if some factory is here, or if some factory is here, for these two guys, the best is to go this case because it is the least distance they could travel. And if this is not possible, they could go with the one which is minimum distance from the, like the one which is at closest distance from these two. This is the core logic in case of two people, right? If there are two people, it's better to choose the factory which is here in between them. Oh guys, I this is a very beautiful intuition, I would say. For two people, it's favorable to choose the factory which is between them. Oh man, how could I miss this? Now see this. These people, no matter wherever this factory is located between these two guys, the total distance traveled by them, if they get, so there is an assumption. Uh, okay, so the total distance traveled by them, the assumption is that they should get moved to the same factory, right? In that case, the factory should be between them, and it could be any one of these. If they can, they have choice. Man, too many trackers here. Let's check if I can hear these in the live stream. I think it has already taken a lot of, and it could be any one of these. If they can, they have joined too. Man, too many crackers. So now live, you guys cannot listen the crackers which I listen outside my house. Now these two guys can go to many factories. Mhm. If some group of people choose this factory, it could be like this. Yeah, if some group of people chose have chosen this factory, some group of robots have chosen this factory, that means mhm. So isn't it giving me a approach that yeah, that means like the answer is distance between them. Distance between these two, and this guy is alone. But no matches. Basically, the distance between two guys. That is again a subjective thing. Okay, let's come to DP approach. How can I break this problem to subproblems? Okay, so yeah, so the problem was this also. For each robot, you decide the direction of movement so that the distance is minimal. Problem with this approach was that actually did it. There's no direct competition. So I clearly skipped this case as well. That there are two robots and there is some particular node here and there's only one seat, some particular factory here. Now this is the distance 1, this is the distance 4. And if you choose this configuration, right, it is failing. It is failing big. Now you're like exhausting your mind thinking that this guy has potential to reach this. But in reality it's not. Once you decided that, this guy will just go to this factory and get repaired. This has never got any chance to visit this, right? Yeah, it makes sense to me. So wait, I have the factories written here, F1, F2, F3. T equals to 0, T equals to 2. Now I have to think that robot R1, some factory F1 is here, robot R1 is here, robot R2 is here. Both of them are at the same locations. So any one of these can play. I hate this problem to be honest. So what is this? P position of the factory. All robots are initially dead. Yeah, I know that. Unique positions. Unique positions of factory means what? Yeah, that is just kind of nonsense, right? There is like at the end, there is one possible. Yeah, clearly there is there is some game of movement as well. So basically, this part is very much crucial because you cannot just randomly put robots at the factories. There is some sort of direction which plays a role, which is predetermined at the beginning, and that decides the direction only decides that which robot will get where. Right, so if I try to continue this particular thing here, it's crazy long video. This particular thing here, so for each level, for each robot, I got to decide 0, 1. Hmm? 0, 1 is the directions, right? The moment I specify a direction 0, this robot starts moving this direction, in this direction. And let's say this position is basically sorted. So by setting it 0, it means I have shot this rocket to this side and it will land at the first factory it has seen. And that will basically change the configuration. Now, basically, if I go to this step, there I had two more options. This way also, the rocket could be shot here as well, and it could land at the nearest factory, which has some limit left. Fair enough. These are the two possibilities. After this, we got some configuration of factories, which is in the order 10 to the power 2. Now, this will be shorten up. It has also got two options here, and it will also destroy some guy. Now, again, this is like two choices each level we have. This can also hit somewhere. Two choices at each level, and this goes into 100 times. So it is like the entire thing is 2 to the power 30, and I don't know how to cache it because caching it means breaking down into subproblems, and Is there a kind of recomputation I'm doing anywhere? Basically, I'm not recomputing it, or am I recomputing? Basically, this is the factory configuration which we have, and when I decide a direction, it means that these factories will get impacted. If I decide this direction, these factories will get impacted. Now, this guy can go 0 or 1, 0, 1. This can go 0, this can go 1. Yes. And this is a kind of separate thing. After that, yeah, this is a separate subproblem. And chances of it to repeat, which we look in DP, is quite good. It's quite good. Can I do it like that? But this side will incorporate this incoming rocket. Okay, so let's say for a particular robot, if I set this to go in this way, so it will cover from this index towards the end of this array, right? And let's say we had, so this is, guys, I'm talking about its physical location as well. So let's say this robot has got position 10. Now we are interested in the factories from this position 10 towards the end, right? And yes, so we are interested in this kind of calculation here. And let's say earlier from here to here we had X number of spots. Now when we shoot this guy, problem will now change to, yeah. Let's say there is one more guy which was shot here before this. It means it has to be placed in this region, right? So this guy could have placed here as well, but it could be placed in this region only, right? So it means that this entire region had count somewhat high, right? And if I shoot these two guys here, it became y minus 2. So I shoot this guy. Hmm, I don't know, man. So let's say we are at the end of the factories. If some guy is alone here, this guy will get to the fifth shot from here. This guy will get to the nearest factory. Okay, get that way. Let's say if we have very much. So this is all the indices on x-axis. Let me do like this. And robots are somewhere here. So robots will also have some order. This robot can be shot here, can be shot here, right? So if we shoot this to this side, it is guaranteed to land here. Now if we shoot this to this side, and then it's not guaranteed where it will land. Why? Because this also matters, right? If we had shot this to this side, then there will be kind of race between these two. The one which is closer will win. So basically here we can surely say that this guy will hit this. But if we shoot it this side, then it's a kind of race thing. Okay, so if we shoot this guy this side, then it is guaranteed that this guy will attack over here. Now DP कैसे लग सकता है इसमें? Particular region में I was thinking right region wise, like there could be conflicts. And if we particularly see these factories in this region, at the end there will be mixed reactions, robots, which constitute the final solution. Guys, really, I don't want to spoil my day, so I could not solve this problem today. Really, very sorry for this. But in the next video, I'll be starting from right here. And so, one announcement, I'm going for a trip for 3 days. So, after 3 days, I will continue from here. Sorry, guys, it was Diwali, so I did not want to spoil my day, and I am quitting this problem for time being.